Hello Internet! Today a little bit about tensor algebra. Why do we need this? Here on the right side, we have a neural network model. And let's say we have our input data, and the input data have the form, of course, of a tensor, and then we have layers. And let's just look at one simple layer, and you could ask yourself, hey, if I have, like this here, the data in a rank 4 tensor, how the hell does this input data will fit into this planar layer? What is the dimensionality of my nodes, of my units? How does this fit here into a layer operation with a rank 4 tensor? What is the tensor I will get out of the layer calculation after I applied the layer like a function to this tensor? What about dimensionality that will not fit? Or what about I do an operation on an axis I'm not supposed to do? And by the way, where's my feature vector in this rank 4 tensor? And where's my batch axis? To answer this question, let's start with tensors. 5 minutes and you know everything about tensors. Now, the easiest form of a tensor, it's a rank 0 tensor, and it's just a number. TensorFlow.constant 4. This is it. This is a rank 0 tensor. You can call it a scalar. And it's a tensor 4, shape, nothing. Now, the next higher level tensor is a rank 1 tensor. And you know this as a vector. A vector has a component x, y, and z. And it gives you, for example, an object in a 3-dimensional coordinate system. So you say that TensorFlow.constant. And we have here the x, the y, and the z coordinate. And this is a rank 1 tensor. And it looks like TensorFlow tensor, yeah. And the shape now is, since we have x, y, and z, the shape is 3, comma, and then nothing again. So careful about the shape. And of course, you have to take care about the d-type. If you have integer or float, whatsoever, you can define this. So the next step is, of course, a rank 2 tensor. And a lot of people say, hey, a tensor is just a matrix. No, a tensor is an n-dimensional array. We can go much higher than a rank 2 tensor. This is a rank 4 tensor. So a rank 2 tensor is a matrix. It has 2 axes. A matrix like you see here, 1, 2, 3, 4, 5, 6. We have a 3-axis and we have a 2-axis. And if you write this in a Python notation, you have TensorFlow.constant. And now you see we have 3 objects here. And within, those are 3 objects. And within these 3 objects, we have, if we take now the first object of those 3, we have another 2 objects. So 2, 2, 2. So we have 3, 2 as the shape of this tensor. Summary. A scalar is a shape 0, a rank 0 tensor. A vector is a rank 1 tensor. A matrix is a rank 2 tensor with n-dimensional arrays. Now, we can have more axes. Here is a tensor with 3 axes. How we construct it? Easy. We say same notation. We go here with double parentheses and we check out where does it open and end. Here, open and end. Double parentheses, open and end. So I know we have 3 objects. Then I know I take the first object from my 3 and I see, okay, I have 2 lines here. So this is 3, then 2, and then I take the line. And in my line I have 5. So I have 3, 2, 5. My 3-axis tensor has the shape 3, 2, 5. Just have this in TensorFlow. If you see an object like this, this is very easily a rank 3 tensor with the shape 3, 2, 5. And if you want to see the numerical data shaped, because data have shape, data have structure, and it's an integer 32, you can have here, and it's a little trick, just look for the first granular is if you have this, look at how many elements you have. For double parentheses, we have 3 elements. And then I take the first element, and then I have a look, okay, and how many objects I have here? And I have 2 lines, so 3, 2, and in the line I have 5 objects, 3, 2, 5. So if you want to imagine this, easy. You can have a planar datasheet. And you have it either in this way, or you have it stacked in this way, or if you prefer not a planar datasheet, but you have a cube. And this is what we're going to run if we go in a higher dimensional representation. This is the way to go. Now, what is this? Very easy. This is if you take a picture. And your resolution is you have a picture with 10 pixels, from 0 to 9. And you have the red channel. Then you have the blue channel. And then you have the green channel. And you have an RGB picture with 10 pixels in each channel. This is it. This is what you can see here. But be careful, because the axis you choose will be important later on. So this is a shape 325 tensor, a 3-axis tensor, or a rank 3 tensor. And of course, you know it's almost the same as NumPy, because NumPy runs on a CPU. But we now, when we construct our neural network models, we want to run our arrays now on a GPU, or even better, since it's tensor algebra, we want to run on a tensor processing unit, on a TPU. But we can transform it forward and backward. Just say numpy array, or if you have the tensor, say .numpy, you can transform it forward and backward. Yeah, rect and sparse, we don't need this. Now the beautiful thing is, a tensor is not just a tensor in itself, but you can do mathematical operation. You have addition, you can have element-wise multiplication, and I'm sure you are familiar with matrix multiplication. So let's have a look at this. We have 2 tensors, a tensor A, very simple tensor, and a tensor B. Tensor B is just identical. And then we just add the tensor. So what you say is TensorFlow.add tensor A and tensor B. Or you can have an element-wise multiplication. So each element is multiplied with the element of the tensor B, tf.multiply, or you can have matrix multiplication. Remember, this is something else like an element-wise multiplication. And here you have TensorFlow.matmul, tensor A and tensor B. Very easily done. Say, if you add the tensors, easy. Just add 1 to each element. If you multiply the tensor by an identity, if you do an element-wise, easy. And if you do a matrix multiplication, of course, it will have the matrix structure. Now, what you have to be careful, and this will happen if we do the layer operation from our tensor input data, we will operate with tensordot. And tensordot, you have to distinguish between the operation on the axis. For example, if you have tensordot on axis 1, so you have the operation TensorFlow.tensordot, the command, then you have the tensor A, the tensor B, and you specify a long axis equals 1. And you will not believe this, but this is equivalent to a matrix multiplication here. But if you say tensordot along axis equals 0, this gives you the outer product. And it multiplies the dimensionality. You have now a tensor of order 4. So you see here, if we do here the tensordot on axis 0, we have an outer product, a tensor product defined. And of course, you can have not just stick to the real numbers, but you can have complex numbers. And then you are familiar with this. You have the complex conjugate or the transpose. So if you have a multiplication of the tensor V with the tensor W transposed, this is more or less our tensor product that we defined. Easy. So again, tensor A and B, A times B, and element-wise and matrix multiplication, beautiful. Yes, the shape of a tensor is important because A vector, as I told you, in TensorFlow can have only one shape parameter. Remember, where's my vector here? It's a one shape parameter, 3-dimension, x, y, z. But it can also be here in a matrix a column. Now, watch out, because if you treat it as a column, you say vector 1 is tf constant shape 3, 1. So now you specify it is the column of a matrix. And you have another vector. You can do the mathematical multiplication. You can take the transpose, for example, and you have the inner product defined. And you know, especially doing a layer operation, the inner product is so important, also for cosine similarity and whatsoever. So we have with TensorFlow operating on our input data in a tensor structure, in an n-dimensional array structure, we can do a multiplication. We have a multiplication defined. Isn't that beautiful? And you see that if I have math multiplication from vector 1 and vector 2 defined as a column of a matrix and do the transposition, I get 50. This is it. What else? Tensors are used in all kinds of operation. And let me show you. We have here a tensor. And if you say, hey, find me the largest value in this tensor, well, easy. As you can see, it is 10. So it first gives you 10. But then you can find the index of the largest value. Well, of course, shows you the index. But then you can compute the softmax of a tensor. Not of a layer operation, but simply a tensor. And this is nice, because have a look at this. We have a constant tensor, 4, 5, and 4, 5, and 10, 1. So if you say softmax, remember, softmax operation, or if you want categorical operation to show you the maximum likelihood, the probability, we see that we have here a dominant 10. And remember, softmax was always if the duple or triple, that they sum up, give them a probability operation to 1. So if we have here 10 and 1, we expect here a high number for the probability and here a lower number, but the sum should be 1. So let's do this. And as you can see here, this is what we get. Now, for the second element, we have, this is our 10, 1. We have 9.9 e minus 1 and 1.2 e minus 4. So if you do now convert this to float, you can see the last two, yes, perfectly, they sum up to 1. Now the same happens, of course, to 4 and 5. Now 5 has a higher probability calculating the softmax, but just a little bit, and they both should add up to 1. And here they are. You have for the 4, you have .2689, and for the 5, you have a probability of .73, and if you add them together, you get 1. So you can have a softmax operation on a TensorFlow constant on a simple tensor. Compute softmax activation, multi-class prediction, it's 1. Yeah, you have the notation, you have the logics, you have the axis to be defined, you can give it a name, and the operation that it does is simply this mathematical formula. Yeah, logics on non-empty tensor must be one of the following types, float 32 or float 64. Axis to dimension would perform indicates the last dimension. Yeah, now to the shape of the tensor. And this is important. Tensors have shape. This tensor here on your right-hand side is a rank 4 tensor. It has a shape. Data have shape. Now, the length of each of the axes of a tensor is a shape. The rank is the number of tensor axes. We have 1, 2, 3, 4 tensor axes, so we have rank 4. The axis or the dimension are a particular dimension of a tensor. So we have here 3, 5, 4, 2. And the size is the number of items in the tensor. All those little cubes, how many cubes do we have? Turns out 120 cubes. So the size is 120. Yeah, you can calculate this, of course. So let's do this. We just take a tensor with 120 elements, and then I do a simple reshape because I want to get a rank 4 tensor. And if you do this, this is the tensor we end up with. This is the shape 3, 2, 4, 5. This is exactly our 3, 2, 4, 5 tensor that we have depicted here. And this is the numerical presentation of our tensor. But if you want it even easier, we can set everything to 1. Maybe then it's easier for you. And you see you have 3 master elements if you want. 1, 2, 3. Those are my master elements, 3. In each master element, I have 2 further elements, 1 and 2, you see here. Then I take those elements, and now you can see here I have 4 lines here, 1, 2, 3, 4, 4 lines. And if I take one line, I have 1, 2, 3, 4, 5 ones. So my shape is 3, 2, 4, 5. Now comes the important part. Now you see this is now exactly the same tensor I have here also on my right side. The axes. The axes of a tensor are important. We start with axis 0, not with 1. We start with axis 0. And this is also called the batch. And the axis, the last axis, is the axis -1. And this is the feature. So if you want to know the batch size, the batch axis, and the feature axis of your tensor, it is the first and the last one. And the one in the middle, if you want, are the dimensional ranks, dimensional axis. So rank 4. Let's do this. How can you calculate this in Python? Now easy. Yeah, let's just execute it to show you. So the number of every element is, the D type is float 32. Beautiful. So the number of axes is simply tensor.ndim. So the number of axes that I mentioned is 4. 3, 4, 5, 2, 4. Now the shape of the tensor, we just showed you, is 3, 2, 4, 5. And now you can ask for the element. Shape is of course tensor.shape. And then you can ask for the element along axis 0. And there you do also tensor.shape at 0. Shape 1, shape 2. So you define the elements along specified axis. And of course, the last axis of your tensor, as I showed you, if you are not sure how many axes the tensor have, but the features are normally the last one, just say shape -1. Then you get the elements along the last axis of a tensor. And if you want to have the total number of the elements of a tensor, it is simply, you say TensorFlow.size of the rank. And if you want the numpy. And this is what you get exactly. You have 120 elements. And then for the nomenclature of the axes. And this, please remember this. The axes are often referred to by the indices. So the first one is called batch. The last one is called features. The batch axis first, followed by the spatial dimensions, and features for each location last. This way, the feature vectors are continuous regions of memory. You want to make sure they're in the memory. So, rank 4 tensor, like this one here. The first size is the batch size 3. Then we have the dimension, the width and the height, 2 and 4. And the feature axis is 5. So now you are able, with this notation and with this axis order understanding, to understand the dimensionality of this rank 4 tensor. And now in the next video, I'll show you how you have to configure, how you have to build the fitting dimensionality of a layer operation of a function that acts on a specified n-dimensional array, a tensor, in our case, a rank 4 tensor. Thank you, and I see you in the next video.